In this video, we'll consider finding the magnetic field of a short line segment, length L, carrying current I, at a point P, a distance y above the midpoint of the wire using Biot-Savart law. And so let's dive right in. As our first step, we've always said, draw your picture. We've got the initial diagram of our wire. And so the next part of drawing the picture is, of course, indicating a segment of our wire, DL, with its corresponding r hat pointing towards point P. And then step 2, we're going to immediately jump into computing dl cross r hat. And so dl itself points purely to the right, so we're going to rewrite that as scalar dl I hat. And then we're taking the cross product with r hat, which we can decompose by introducing an angle theta right here. R hat itself has magnitude 1, and so its components will be cosine theta I hat plus sine theta j hat. And so now remembering our convention for the cross product, ijk, I crossed with itself is 0, so dl I hat cross cosine theta I hat just goes away, and dl I hat cross sine theta j hat becomes dl sine theta. And I hat cross j hat, following our arrows, just gives us k hat. And so conveniently, all of our contributions to the magnetic field at point P point in one direction. We don't need to do any vector decomposition. We only need to do one integral. And so let's move on to step 3, which is setting up our integral. We have dB is equal to u naught I over 4 pi integral dl cross r hat, which is now dl sine theta over r squared. And at this point, we ask the usual question when we're looking at an integral. And of course, we should have the integral on the other side as well. And we ask our usual question, which is, does anything vary with respect to the variable of integration? And in this case, unfortunately, it does. We can see that our distance from point P changes as we go along the wire, as does the value of theta. And so for that reason, we need to introduce a coordinate system. Looking at our diagram, we can see that dl, our arc length, is purely aligned with the x-axis, so we'll simply say that dl equals dx. And then to take advantage of the symmetry of the problem, I'll place x equals 0 right at the midpoint of the wire. And so with that, let's try rewriting everything in our integral in terms of x. We'll begin by stating, and let's bring our diagram down. We'll begin by stating that our integral is mu naught I over 4 pi. That has not changed. Our variable of integration is now dx, and our job now is to rewrite sine theta and r squared in terms of x. So let's consider an arbitrary point at a distance x from the origin. We can immediately see by Pythagorean theorem that r squared is simply x squared plus y squared. And then we can see that sine theta, if we place theta right here, is y over squared x squared plus y squared. And lastly, our bounds of integration will go from negative L over 2 to L over 2. Now, actually solving this integral would require trig substitution. So I'll leave that as an exercise or address this in a separate video if there are any questions on this. And that is exactly why we have the motivation to develop a different technique for doing this problem. Now, if we consider this a short line segment, we do not have any other techniques, but let's imagine making the segment infinitely long, or considering the field at a point very close to a short segment so that it appears infinitely long. This is where we'll develop an alternate approach to finding magnetic fields, known as Ampere's law, which we'll address in the next video.